Good morning, everybody. This is Dr. Ehab Mina. I got my PhD back in 2001, and I did serve as associate professor in Survey Research Institute, National Water Research Center in Egypt, and then I did move to United States from 2005, and I did serve as Director of Survey Surface at MJ Engineering and Land Surveying. Today's topic is the network adjustment. I will be very specific about the GPS networking, and the topic itself will be about how to adjust the GPS networking, even if we combine two different techniques of GPS observations. First of all, let us look at the screen here. This is how we build our network. A baseline connecting each point, and applies a standard for observation, and the number of baseline should be out of each point. And you can easily see that we have the outer monument encompass the project here. This is mostly the NGS monument, as well as the rectangular squares here, which represent the NGS benchmark. So once we have this figure, we need to establish a primary control for center project and be tied to the system, the network, the local system, or the state system, or even the national system. And after the processing of all these baseline and establish this network, we need to refine and enhance everything and do whatever called the adjustment to get a unique coordinate for each of these 6 points. In principle, we can divide the adjustment procedure into 2 main steps. The first one, we call it the free adjustment or minimally constrained adjustment. And the second one is the fully constrained adjustment. Let us talk first about the minimally constrained adjustment. You can see from the name that it's a free adjustment, which means that there is no fixation, no holding of any control, NGS monument, or even the newly established coordinate. We are doing free least square adjustment. And the task, or the main task here, is to check the internal consistency of the network and detect the blunder, or what we call it L-fitting observations, and also to obtain an accurate error estimates. The error estimates here, it's very important because we have, before we enter this process, like we hypothesize that we have different weight or certain weight for the measurement, but during the observation itself, we do have like different conditions. So we need to scale our errors to be able to get successful statistical evaluation for the network. So if we get the network like that, we don't fix any of those monuments, but we will use an state to fix internal measurement, any baseline, or nowadays the modern software will choose that for us. And we hold those measurement, and we run the least square adjustment, and then we judge the statistical result of the chi-square test, which is responsible for show us what is the success evaluation of our error estimate. And we have to remember here that in that phase we are filtered out the blunders, no systematic errors, and we have our figure, our geometry of the network very rigid and well consistent. Let us talk now about the second phase, which is the fully constrained adjustment. In fully constrained adjustment, we need to reference ourselves to the existing control, to the system, as I told you before, and also verify the existing control. Maybe we have one bad control and interrupted or something like that. And also we need to produce the network transformation. So we will start with like one point, fix it, run the least square, and then check the consistency. And let us review again what we need for this adjustment process to happen. We need, as I told you, like certain parameters to to perform this phase. The parameter is, all in all, 7 parameters. If we break it down, it would be 3 rotation, 3 translation, and the scale. So we need 7 parameters. Let us remember something, that the horizontal point gives us 2 equations, 2 parameters, x and y, and the vertical benchmark gives us 1 parameter. So for us to have 7 parameters, we need 2 fixed horizontal points and 3 fixed vertical points. Nowadays, the situation is more enhanced, more easy. So we can see that we should have 3 of the 3D dimensional point, which have the x, y, and z as well. So we can use 3 of them, give us 9 equations. So we use 7, which is necessary observation, and the other 2 will be as a check for final evaluation and use it as redundant observation. This is the how we do our translation and rotation to do the transformation, and in this process we make our network be consistent with the system. More control will add, as I told you, more control will add more confidence to our network and our adjustment process. And again, I have to remind you here with the principles of GPS that we need also to get the elevation to adjust the new network in height. So let us remember that with each other. Remember that we do have 3 main surfaces. The first one is, the middle one is the ellipsoid. The ellipsoid is imaginary surface, all the calculation, all the computation of GPS is referred to that surface, but we do have the actual ground, the actual Earth's surface, and also the as a datum or as our reference for elevation always is the geoid, or what we call it a geoid. The geoid is representing the mean sea level, or let us talk in simple and say now it resembles the mean sea level. So we have to find here the relation between these surfaces. The relation is given here. Elevation equal the ellipsoidal height minus geoid undulation. So we do have the capital H from the GPS measurements itself, and the N we will get it from the geoid model. And this way we can get, nowadays we can get the elevation by this equation within plus or minus in the United States of 2 centimeters. So the geoid model is the best fitting for the the elevation for the mean sea level, and all the software give us the geoid model. It's already geoid model. We have now the 2003 and 2006. We have like enhanced model, like every 3 or 5 years or so. Next step is the datum transformation. We know that GPS use WGS84, and we use in United States or any state or any project, it has local system. Let us talk nationwide. Nationwide, we use NAD83, and now we need to convert the GPS measurements from WGS84 to NAD83. The following step is to convert the spherical coordinate, latitude and longitude, to the plane coordinate. Knowing, all the engineering, all the project need like metric. Nobody will work with like a spherical like coordinates. So the step is to do this conversion from a spherical coordinate to the plane coordinate. So we have to choose here which projection we're gonna use. All the United States has zones, and on the software you have to choose the proper zone with the proper projection to do this step. Now, before we finish this presentation, let me summarize the main principle we need to stress on them. So, adjustment, this is the process we deal with certain amount of error. No systematic errors should be entered to least square adjustment. So mistake and systematic errors must be removed before the adjustment. And I'm reminding you also that a least square adjustment handle just random errors and provide a single solution. The minimal constraint adjustment checks the internal consistency, as I told you, the rigidity, the consistency of the figure itself. And in fully constrained adjustment, we transform from WGS84 to local. We also reduce the spherical coordinate to certain projection, and we also adopt the a proper joint model to adjust the third component too. So I know it's a very very simple presentation. I didn't go in details, but this is like, a summary of the steps of the network procedures that we need for each typical GPS networking. Um, Thanks for that, and if somebody has certain question, can contact me. Thanks, and have a nice day.